Okay, so now we're going to talk about the fundamental theorem of algebra. This is actually something that you have seen a lot already. We just didn't formally address it necessarily. You can see the formal definition of the fundamental theorem of algebra in your note packet right above at the beginning of this section. But essentially what it says is that every nth degree polynomial has exactly n zeros. And if you look back at every single example we've done where we're finding the zeros, that comes out to be true. So what is the degree of the polynomial? That's how many zeros you should have in the end. Remember, way back at the beginning of this unit, we talked about possible number of real zeros. That was also the degree. But now we're talking all zeros. So there will be, whatever the degree is, that number of zeros. They might not be real, they might be real, but there will be that many zeros. We've already seen that in every example we've done. Okay, so a lot of these examples I'm going to just have you work because you've done things like this before. So I want you to find a polynomial with the given zeros, 4, 3i, and negative 3i. Pause the video, find the polynomial, find a polynomial. There are many correct answers. Find the simplest one, though, I'd recommend. And unpause when you're ready to check your work. Okay, so the simplest solution is f of x equals x cubed minus 4x squared plus 9x minus 36. How do we come up with that? Well, if 4, 3i, and negative 3i are zeros, then I know x equals 4, x equals 3i, and x equals negative 3i, which means x minus 4 equals 0, and x minus 3i equals 0, and x plus 3i equals 0. Therefore, all of these are my factors. So I say f of x equals the quantity x minus 4 times the quantity x minus 3i times the quantity x plus 3i. I did not say you had to multiply this out, but it's good practice to multiply it out most of the time. And sometimes I'll tell you specifically to do that or not do that. But so I multiplied this out to make it into a nice polynomial function. Alright, find all of the zeros and write the function in completely factored form, or as a product of linear factors. Do this however you want. Pause the video, unpause when you are ready to check your work. Okay, so the zeros I get are plus or minus 3i and negative 1. I did this by factoring because, again, I recognize by looking at this is going to factor by grouping. You could have also used a calculator to get the negative 1 and then done synthetic division to find the plus and minus 3i. So those are the zeros. I also wanted to write this as a product of linear factors. So remember, we've done this already. That would just be writing this as f of x equals x plus 3i times x minus 3i times x plus 1. So this is a product of linear factors. Next one. List all of the possible rational zeros. Then find all of the zeros and then list them in linear factored form, or that's the same as writing as a product of linear factors. Pause the video, do this, unpause when you are ready to check your work. Alright, so we should end up with x equals 2i, x equals negative 2i, x equals 1, and x equals negative 1/2 as all of our zeros. The possible rational zeros, so again, make sure you're answering all parts of the question. So possible rationals, factors of the constant term, so plus or minus 1, plus or minus 2, plus or minus 4, over the factors of the leading coefficient, plus or minus 1, plus or minus 2. Now, how did I find the zeros? So I used my calculator. I put the function into my calculator, so you can see I have the function in here. I looked at the graph, and then I did second trace and 0 to find the two zeros that I can see on the graph. And so this one was negative 1/2, this one was positive 1. So I used the calculator to get as much of that as possible. Then I did synthetic division with those two zeros. So I did it first with 1, then I took that quotient and did negative 1/2 with those coefficients, and so I ended up with 2x squared plus 8 as my quotient. So then I set that equal to 0, and that's how I got the plus or minus 2i. So these are all of my zeros. Now the next question. Write this as a product of linear factors, or in linear factored form. So I have another question for you then. Which one of these is correct? Only one of them is. So the red or the green. There's only one difference. It is a slight difference, but it is an important difference. So one of these is correct. Dramatic pause, right? So which one is correct? Well, if you haven't figured it out already, spoiler alert, it's going to be the red. Why though? Why is this one correct as opposed to the green? So there is a difference. They both have the same exact zeros. If I found the zeros of the green, it would be the same as the zeros of the red. It would be my answers here. But the red is correct because if I look back at the original polynomial, the leading coefficient was 2. The only way the leading coefficient is going to be 2 is if one of these linear binomials has a leading coefficient of 2. So that's how I know that the red one has to be correct. So you want to be careful about that. Alright, next one. Find all of these zeros. Pause the video, find the zeros, unpause when you're ready to check your work. Okay, so we find that all of the zeros are x equals 0, x equals plus or minus I root 3, and x equals plus or minus 1. Again, pointing out fundamental theorem of algebra, degree was 5, we have 1, 2, 3, 4, 5 zeros. So we have 5 zeros. This one, again, I just did by factoring. I recognized there was a greatest common factor of x equals 0, of x, so I factored that out. That means x equals 0 would be one of my zeros. And then I get this x to the 4th plus 2x squared minus 3. That factors into x squared plus 3 and x squared minus 1. Again, you could have used your calculator to get the 1, the negative 1, and the 0 and done synthetic division, but if it factors, that's probably going to be quicker and easier. Okay, so now the question comes up on your packet. What do you notice about the complex zeros from all of the previous examples? And in fact, every example we've done ever. Any ideas? So pause, write something down. Okay, hopefully you notice that they come in pairs, or more specifically conjugate pairs. So what does that mean? That means that anytime we're going to get complex zeros, they're going to come in pairs, so that's going to help us figure out how many real zeros we're going to have. This is only true if the coefficients of the polynomial are also real numbers. However, for what we do in this class, all of our examples will have coefficients that are real numbers. But then we want to understand complex roots come in conjugate pairs. The same is true for irrational roots, and you may have noticed that already. For example, if I get the square root of 2 is a 0, I'm also going to have negative square root of 2. So, why is that important? Well, if I say x equals 2i and x equals 2 are zeros, and I want you to find a polynomial with real coefficients, then if x equals 2i is a 0, you also know x equals negative 2i has to be a 0. So a polynomial would be f of x equals x minus 2i and x plus 2i and x minus 2. We could multiply this out again, but that's not the point of this exercise. The point of this exercise is to recognize that if I have to write a polynomial with real coefficients and one of the zeros is complex, then the conjugate pair of that number has to also be a 0. Okay, so every nth degree polynomial has exactly n zeros. Fundamental theorem of algebra, essentially. Complex roots come in conjugate pairs. Use the calculator and possible rational zeros to find some roots and then do synthetic division if it doesn't factor.